Okay. In this course, our ultimate goal is a quantum computer. To get to a quantum computer, we're going to start with what you know and love, classical computers. What we're going to do is we're going to quantize the computer, right? So we need a model of computation before we do that, or at least an abstract one. So the three fundamental guiding principles of that model and three motifs of this course are going to be state, information, and computation. Now, when we switch from classical physics to quantum physics, these three things are going to change dramatically, right? So that's why we're keeping them as the underlying principles. The idea here is we want this model of computation that depends on an underlying physical model. And when we change the underlying physical model from classical physics to quantum physics, we want the classical computer rather, to change to a quantum computer. And to understand that transition, we're going to need to really understand these three concepts. So let's get started on that. Okay, state. What do we mean by state? Well, state is essentially a system. You got a system, S, and that system has variables. Let's say we're dealing with a physical system. That's going to kind of be our go-to example. Um, we have things like position, we have things like velocity, we have things like energy, we have things like temperature, all those kinds of things. Those are variables of that system. And when we specify them, give them each a unique value, we're specifying the state of the system. So a little bit of terminology here. State space. The state space of a system is just kind of a list or a set. That's what this curly notation means of these variables here. The variables that uniquely specify a system. So if I give you a value for each of these variables, then we know the state of the system uniquely. That's pretty much all it means. So this is just going to kind of look like this. x1, x2, through n, if there are n variables that uniquely specify the system. Right? So a state configuration is actually filling in the values of these variables. State config is just kind of the same thing, but they actually have concrete values now. Let's call it symbol I. Right? So this same kind of thing with all these filled in. Okay, so that's kind of what we mean by state abstractly. Now, you might wonder which variables matter, right? When you say specify the state of the system, it's almost a recursive definition. What do you mean by the state of the system? What variables are relevant to the state of the system? Well, to answer that question, we're going to need a model. Um, we can model a computer, we can model a physical system, and in fact, we would like a model of a computer, and we would like it to depend on a model of a physical system. And as we were saying at the top of the lecture, when we transition from classical to quantum, we want to see both models change in a reasonable and predictable way. So let's give an example of a physical system model. The simplest one possible, the 1D point particle. What's the state of the 1D point particle? Well, what's its state space? In Newtonian physics, we need position and we need velocity to uniquely determine the system, right? This is starting to kind of make sense. These are the relevant variables as per the model of Newtonian physics. Because once we have these two guys, we can plug in F equals ma and determine the state of the system for all times, right? 1D point particle. What's an example of a model of a computer? Well, in keeping with this really simple idealizations, we're going to model probably the simplest computer I can think of, which is going to be an abacus. You got these little beads on a string and you move them along to add and subtract, right? So this is the model, this is our model of a physical system. And the abacus is going to be our model of a computer. And we want these two to be related in a very specific way. We want what for this course we're going to call a physical model. We want our computer to be modeled by a physical model. And the way I'm going to define that is a physical model is a model, the state of which is uniquely determined by a physical model, or a model of a physical system rather. Don't use the definition, the word in the definition. Model of a physical system. I'm defining a physical model. Right? So we have this abacus here, and we want its state at any given time to be uniquely determined by a physical system. And we have a nice candidate right here, actually, the 1D point particle. There's a natural correspondence between the 1D point particle and the abacus, actually. If you simply map B to particle, there's your correspondence. There's your isomorphism, right? Because these beads go along a rod, so it's just one-dimensional. It can only travel in one direction. And in fact, we can forget about the velocity and just focus on the position because that's all that specifies. That's the abstraction, right? We abstract away from the physical model. It's more abstract than the physical model. The way you can think of a model is almost like a wheat chaff filter, right? You have a system, and only some of the things about that system are relevant. Certain things about that system are irrelevant, and we don't care about them. This depends on the model. This depends on the situation, which depends on the problem we're trying to solve. So the velocity is not relevant, so we filter it out with an abstraction, and we call that abstraction a model. That's pretty much all we're doing here. But recall that this model of the abacus had better be a physical model, in the sense that at any time its state is uniquely determined by a physical system, and the physical system is the 1D point particle, right? So we have the abacus, and we have its state. Its state is the same pretty much as the 1D particle if you just omit velocity. I'm not going to write it out. But at any time, the state of the abacus in this model had better be uniquely determined by the physical model, a physical model. In this case, it's just Newtonian mechanics with the position of a 1D point particle. Right, you see that? So we want a computer to be determined by an underlying physical model. That is, we want to have computation, state, and information as fundamentally physical concepts. And the way that we're going to enforce that is by forcing our models of computation to be physical models. So that way, when we go from classical to quantum, you're going to see the physics change, and you're going to see how that changes the nature of the computer. I think that is a good way to jump into quantum computing. And I think throughout this course, and the literature in academia on quantum computing is kind of already here, in terms of this philosophy, right? We kind of already see information as physical. We see state as physical already because physical systems, what physicists are dealing with all the time. So when we kind of started studying quantum computers, we noticed that these correspondences always kind of line up, actually. For a quantum computer, the way we compute is by changing a physical system, a quantum system. In classical physics, it's not so obvious. In quantum physics, it's going to be super duper obvious. So we're going to enforce this kind of physicality in this way. Right. So now that we have that on the table, right, now that we have kind of the paradigm and program for this course on the table of what we're going to be doing, let's jump into talking about state information and computation, right? Classically. We're going to start classically. That's what this lecture is about. Okay, so what's classical state? Um, we kind of heuristically went over what classical state is up here, state space and all these sorts of things. But what we're going to do actually is we're going to represent state information and computation as mathematical objects now, bringing in the power and versatility of math so that we can discuss the relationship between these concepts and how they affect each other and how they're derived from each other. So we kind of know what state is now. Now let's mathematize it. Let's make it into a mathematical object. Now, state's going to be a vector. And computation, see if I can spell computation. Computation is going to be a matrix. And information is going to be a vector as well. Okay. So state, we define state above. See above. Okay, what about computation information? I haven't really talked about those yet. So before we mathematize them, let's get kind of a intuition for what they actually mean and a definition for what they actually mean. So for the purposes of this course, I'm going to define computation in this way. I'm going to model it, if you will, with this definition. Any operation or process that changes the state of the system. Okay? And information is just what an observer knows about the state of the system. Okay? Now to make it into math. What's your typical state vector going to look like? Well, there are a couple of different classes of state vectors that we want to talk about. But in general, let's talk about a coin. You got a coin. There's two possible states. Heads, tails. So if it's in a state of heads, its state vector will look thusly. I apologize for using that word. Tails, the opposite, right? Okay. So from this picture, you can kind of see intuitively what we're talking about. There's a 1 in heads, and there's a 0 in tails. So it's probability 1 of heads. Here's probability 1 of tails. Okay. So that's the state vector. Let's do some operations on the state vector. Let's initialize our coin in the state of heads. We're just kind of holding in our hands as heads. And let's say we want to turn the, let's say we want to do nothing to the coin. There's actually an identity operator. Let's say we just want to kind of hold it in our hand and just set it down on a table maybe, right? So let's imagine this modeling. You're holding the coin in your hand and you set it down on a table. This is going to be a mathematical model of that. Okay, so we all know that this is just the identity matrix slash identity operator. So it's just going to give us heads back. Okay. Let's say we want to not flip the coin, but turn the coin over in our hands to tails. Deterministically, it's definitely going to be tails, right? This is a deterministic operation, so we're going to know the outcome of it. We're not actually flipping the coin like that. So we'll initialize it again in a state of heads. But this time, we're going to use a flip operator of sorts on it. You can call that the flip operator, why not, right? 0 times 0, 0, right? So 0. 1 times 1 is 1, plus 0 times 0 is 0, right? Okay, so now we're in a state of tails. So the flip operator works, it gives us tails. Okay, these are deterministic operations on deterministic states. As you see, there's a 1 in one of the slots of the variables. Let's say we just flipped a coin and we don't know what state it's in. What does that state look like in terms of a vector? A little bit like this. Probability of heads, probability of tails. Right. This is a probabilistic vector. It represents a probabilistic state. There are also probabilistic operators because we can do things like flip a coin, right? A probabilistic operation is an operation that we don't know deterministically what the outcome is going to be. So we can actually flip a coin and the operator looks like this. You can write every probabilistic operator as a linear superposition or a linear sum rather. Sorry, we're not hiding quantum yet. A linear sum of two deterministic operators or n deterministic operators. In this case, the coin flip operator can be written as a probabilistic weighting of don't flip the coin, 1/2 probability we don't flip the coin, and 1/2 probability we do flip the coin. That's the coin flip operator. Now we're actually doing that. Let's flip a coin. All right, we'll initialize it. It actually doesn't matter how we initialize it. And this makes physical sense because when we flip a coin, uh, the probability of the outcome is independent for each trial. So it will not depend on the outcome of the previous trial. Therefore, it will not depend on whether the initial coin state is heads or tails. Right? 1/2 times 1 is 1/2. 0, 1/2 times 1 is 1/2 times 1 is 1/2, right? Okay. So 1/2 probability of heads, 1/2 probability of tails. This is the state before we look at the coin. So we have a probability of 1/2 that it is in fact heads and probability of 1/2 that it is in fact tails instead, right? So when we observe the coin, we're going to get a different state because have you ever looked at a coin and seen it in 1/2 probability of heads and 1/2 probability of tails? I doubt so. So what's going to happen is upon observing the coin, this is, by the way, not a physical state. It's not a physically realizable state. This is information. So this is actually an information vector, right? Because physically, as I just said, you can't see something like that. It doesn't exist physically in classical mechanics. Um, so making an observation, we can actually take, as we did with the operator, we can use a linear sum of deterministic vectors, right? 1/2 probability, 1/2 tails. 1/2 heads, 1/2 tails. Well, what's the actual underlying state? Well, in classical physics, it is what it is. Regardless of observations, the state of this physical system is the state of the physical system. And it does exist a priori before we make these observations. So once we make the observation, you have a 1/2 probability of it collapsing to heads, and you have a 1/2 probability of seeing tails, these two deterministic states. All right. So that's that's a probabilistic calculation. In computers, it's possible to do these kinds of things in any situation. We have stochastic algorithms, we have things like that, right? So yeah, state, information, and computation. I think we've got a pretty good grasp on these things at this point in terms of classical physics, right? Okay. So yeah, let's talk about one final example to close the state of a digital computer. We want to kind of model that because I gave you the abacus correspondence between the computer and a physical system, but I didn't do it with a realistic computer, like a real, what you consider a computer. So, all right, physical computer, digital computer, you have all these slots here. And our abstract model, this is the abstract computer model. Computer model. You got these things, and they can take two values. You can call it 0 or 1, or you could call it low voltage and high voltage. Because I mean, physically, we're actually going to have these digital circuits that can have one of two possible voltage values. They're microvoltages. They're called flip-flops. They can either be in the high voltage or they can be in the low voltage. And if they're in the low voltage, then the software is going to interpret that as a 0. And if they're in the high voltage, then the software layer is going to interpret that as a 1. And that's how we get binary, and that's how we get bits in a computer context, in the context of a digital computer. So that's your abstract computer model. Um, what's the actual physical system? Well, you can do different types of correspondences. You can correspond between the 0 and 1 abstraction over the voltages. So in that case, the voltages would be the physical system. Um, or you could actually go to the full physical system of digital circuits. You could actually talk about how these, you could talk about semiconductor physics and how these circuits work and all that kind of stuff. But you would never do that when you're actually discussing computation because it's not really relevant. Unless you're in a computer engineering course and you're building hardware, there's no real reason to discuss these sorts of things. We're talking about software and a computer. We abstract away those kinds of details. But the point is that it's there. It's real, it's in a physical system. So these models are always tied to a physical system, right? The same kind of way as like if you think about currency, right? When we had the gold standard, it was always pegged to the value of gold. So in the same way, computers' models are always going to have an underlying physical system to kind of back them in that kind of sense. And that's going to be useful for a number of reasons. One, we can apply physical laws to computation. Two, we have a physical understanding of computation. Three, when we make that transition from classical to quantum, it's going to be really obvious what's changing, how it's changing, why it's changing, and why we kind of get the way the way a quantum computer works kind of works the way it does because of quantum physics. So we want kind of that connection between quantum physics and quantum computer. Um, essentially, what we're going to see when we kind of switch to give you a flavor for it is these bits are the basic units of information and state in classical computing. So the bit, take a value of 0 or 1. They're binary valued 0, 1. Um, in classical mechanics, when we switch over to quantum mechanics, state is going to be very different. State is in fact going to be represented by something called a qubit or a quantum bit, and it's going to have the probability alpha squared of being in a state of 0 and beta squared probability of being in a state of 1 when we measure it. And I'm not going to go too into depth in quantum physics, but state and information are two very different things now. So before we measure it, it doesn't necessarily have a state. After we measure it, it will have a state that will register. But the point being here is this is the connection between the two. So that's why I want you to think about state, information, and computation as three linked concepts throughout the course, all three of which are kind of sitting on a physical substrate. They're sitting on the substrate of a physical model. When you switch that physical model around, those things are going to switch. So what I'm really trying to highlight here is when we go from classical computing to quantum computing, the three big themes for you to look for are how is the state changing? What's the state in quantum and what's the state in classical? And how does it change the way a computer works? Okay, information, same. Computation, this is kind of the core of the issue. How do these operations, when I'm changing the state, now kind of change from classical to quantum? And how does that change the way that a computer's kind of works, is engineered, how the hardware is built, how the software is written, all these kinds of things. So I want you to keep these big three themes in mind throughout the course. And as always, thanks for watching.